This is the Chapter 1-2, Part 2, where we talk about the naming schemes, aka nomenclature, for unsaturated hydrocarbons. So there are three types of unsaturated hydrocarbons we're going to talk about. We have alkenes, and that's any hydrocarbon that has double bonds, hence alkenes. If we're dealing with hydrocarbons that have triple bonds, then we have alkynes. And finally, we have special types of three double bonded cyclic molecules, and they have their own unique properties and therefore their own group called aromatic compounds. Usually we have them separate, but it's possible to have a unsaturated hydrocarbon with a combination of two or three. So for example, in this molecule, it's an unsaturated hydrocarbon with an alkene and a alkyne present. Some of the properties of these unsaturated hydrocarbons. The minute you go ahead and you remove two hydrogens from adjacent carbons, such as in this example right here, they go ahead and form a second bond. So in this example right here, we have an alkene, and the second bond is called a pi bond. A pi bond. It's no longer tetrahedral shape, like we see here in the corner, which I'm circling in blue. Rather, it's going to be flat, trigonal planar shaped with 120-degree angles. The most important characteristic is when there's an extra pi bond, then these carbons can no longer twist and turn. They're in a fixed position. A fixed position. So this will be important a little bit later on. In general, the physical properties are the same as alkanes. So in general, nonpolar, so therefore they're insoluble in water, soluble in gasoline, and unsaturated hydrocarbons tend to be less dense than water. This goes for alkenes and alkynes. We'll talk about the chemical properties later on. I've actually revised these slides and I've taken out the chemical properties, aka chemical reactions, and I've put that into a new set of slides called Chapter 1-2, Part 3. And they're now available if you want to take a look at those. Naming alkenes. First thing I want to point out is it really should say not alkenes, but alkenes and alkynes. So there's a little typo that I'm circling right here. It really should say alkynes. So the first thing you do is you start from the side that's closest to the alkene or alkyne, at which point you can go ahead and start numbering. So think of the alkene or alkyne as a functional group, and that's where key chemical reactions will occur. The big difference between the halogen and alkyl groups is that these are all suffixes when we add in the functional group. So for example, the example on the right that I'm circling, when we include the alkene, we're going to go ahead and change the suffix, which I'm circling right now, from a ane to an ene, to an ane to an ene. So in the example below it, if I'm dealing with an alkene, in this case it would be a 2-hexene, a 2-hexene. I should also point out that this has another mistake on the slide, so you really should be counting right to left. You want to start from the side which is closest to the alkene functional group, so it really should be 1 2. Hence the name is proper 2-hexene. If we take a look at the examples on the left, these are examples of triple bonded unsaturated hydrocarbons. So therefore you change the ene to an ine. An ane to an ine. Excuse me. An ane to an ine. So if I'm starting from right to left, carbon 1 has the triple bond, so it goes from ane to an ine. So the UPAC name for the molecule down below is 1-ethine. The common name is acetylene. So this is a very reactive molecule, and it releases a lot of energy when it combusts. Hence they use these to power the heat in acetylene torches. Let's see a couple more examples using isos. Again, for alkenes, you're going to change the suffix from an ane to an ene. So in this example right here, I'm going to go ahead and turn this into a condensed structure, so you can see the change a little bit better. So in this case right here, we have a pentane. And what I'm going to go ahead and do is I'm going to add a double bond here. Again, to do this, I need to remove 2 hydrogens. So now I've went ahead and I changed it from an alkane to an alkene, and therefore the brand new name is going to be pentene, or pen2ene. A couple of things. First off, the E and Z is another type of what we call geometric isomer naming format. We'll talk about that a little bit later, but we'll use terms called cis and trans. For now, ignore the E and the Z. Ignore the E and the Z. Next thing is, we actually have a couple locations that we can put the location number. It's possible to put the 2 in front, so we can write 2 pentene. Or we can go ahead and put it in the middle. This both are considered acceptable, so you'll see it both ways, both in the book and the slides. My advice is to always put it in the actual name itself, between the parent and the suffix, so that way you can always keep track of it when you have multiple alkenes and alkynes. So in this example, down here, it's the same molecule. Let me go ahead and add in another double bond, so that way we can see when we name this, we're going to start from the side which is closest to the end. And in this example right here, we can see when you have 2 of them, you're going to go ahead and label from the side closest to the substituent. Closest to the functional group. In this case, it'll be carbon 1 here as I'm highlighting it. And then carbon 2, and then carbon 3. Now when you have multiple ones of the same type, you have to use di and tri. So in this case, you would use di, and that'd be in front of the ene. So penta 1,3-diene. Also, when you use di and tri, instead of saying pent, it would be penta. So notice the difference between the top one over here, where there is no A for a single double bond, and then over here, notice there is an A when you have a double, when you have 2 double bonds. Very subtle differences. I probably wouldn't take away points for that, but I just want you to notice those differences. So here I have the same molecule. So it's kind of redundant, so I'll go ahead and remove that one. If we scroll down here, we're going to go from an ane to an yne. So I'm going to go ahead and change this into a condensed structure. And then I'm going to show you changing it from an ane to an yne. Notice you have to remove 2 sets of hydrogens on each of the carbons. I also want to point out for your alkynes, because there are 2 pi bonds, we have a linear shape. A linear shape. So, just to finish this up, alkynes have linear shapes. So therefore, if you're writing the line angle structure, it would actually look like this. So 2 ynes would be a di-yne. A di-yne. So you have to make sure you write it in this format right here. Now, last but not least, as we continue on, you can go ahead and add multiple substituents of different types. So in this case, if I were to sit there and add in a alkyl group or a halogen, I would obey the original rules where, in this case right here, this is a methyl group and it's on carbon 4, so I would have to have it as a prefix. And I'll do P for prefix. For the alkene or alkyne, again, it has to be a suffix. So I do want to point out the alkyl groups and halogens always have to be prefixes, whereas the alkenes and alkyne functional groups always have to be suffixes. Here's a nice example right here where you're using di and tri with multiple of the same type. So 2,3-dimethyl, notice it has to be a prefix in front of the parent. And then here you have 2 alkenes, so therefore it has to be a suffix. Although you can write it like this, I would prefer to have it right between the parent and the suffix. So butyl-1,3-diene. Here's another example here. Let's go ahead and move on. Now, there's actually a little bit harder ones that I could include, and you will see those on the study guide. I could go ahead and have a combination of alkenes and alkynes. So, for example, I could have something like this, in which case you would go ahead and name it, where you would combine the ene first and then the yne second. So let me go ahead and write that in there. With alkene and alkynes both present, the ene suffix goes first, and the yne goes second. So in this example right here, I went ahead and I have a ene and yne together. So it's going to be hex 3 ene 1 yne. So I'm starting left to right. So here's my yne, what I just lassoed, and then here's my ene. Again, I would prefer it so that it is nice and linear, like this. The ultimate hard ones are when you have a combination of enes and ynes together. So I could give you this one as the hardest ones. And let me go ahead and make room here. And I could give you something like this, where I could make it a combination of ene and ynes. So let me go ahead and erase this. And I can make it a combination of ene and ynes. So in this case, hexa 1,3-diene 5-ine. Those are ones you want to play with. Again, ignore the E in front. We're not going to worry about that. Now, moving on, because there is no rotation around a alkene. Let me move back. I'm sorry. Let's go to slide 5. Because there is no rotation around the alkene or alkyne, we have fixed conformational isomers. There are two different types of isomers that we're going to focus on, enantiomers and geometric isomers. I know I'm going all over the place, but let me go ahead and start over. Enantiomers, go ahead and cross out right now. We'll talk about those later on when we get to carbohydrate chemistry. For right now, we're going to focus on geometric isomers, and these are isomers where, due to a double bond or a cyclic structure, there is no free carbon-carbon rotation. So that means substituents are either going to be on the same side. So for example, these are cis, or they're going to be on opposite sides. So think of US being on one side of the ocean, Europe on the other side, so it's trans. That's how I remember it. The easiest way to do this is to go ahead and create a imaginary equator right on the plane of the cyclic ring or the double bond. If they're on the same side, then it's cis. Same side, cis. If they're on opposite sides, then it's trans. So in slide 6, again, we're do a equator right through the cyclic structure or double bond. Same side, it's going to be cis. In this case, for the example on the bottom, opposite sides, trans. Cis and trans are found in biomolecules for fatty acids all the time. So here's an example of a fatty acid. It's fatty acids tend to be really, really long hydrocarbons with double bonds in them. So in this case, if I do a imaginary equator through the double bond, you can see how both of the hydrocarbon tails are on the same side. So therefore, it's cis. If we take a look at this example right here, and I run an imaginary border, these are on opposite sides of the border, so therefore it's trans. One of the marketing gimmicks for food products is that they often say there's no trans fatty acid. And they're not lying. What they're forgetting to tell you is just because there's no trans doesn't mean there's cis fatty acid. And there's also fatty acids where there are no hydrogen bonds, so it's saturated. So, food for thought. Aromatic hydrocarbons. These are flat ring structures with 3 double bonds. And what nature has shown us is that these double bonds in this ring structure, these pi bonds, will actually hop. And they will hop and run around all the way around the ring. What this does is it helps reinforce the structure of this ring. So A, it keeps it flat, and B, it reinforces the structure and makes it chemically resistant and gives it a variety of other properties. We tend to find these aromatic rings in anything that smells, hence the term aroma, where they got the term, such as perfumes. The term delocalized refers to the fact that the pi electrons are not local, they're constantly running around in circles. So for example, here's a better picture showing the pi electrons constantly running around. This is called the aromatic effect, and again it serves to reinforce the overall structure, making it chemically resistant, along with making it very flat. Naming aromatic compounds. This ring right here is so common, and oftentimes what we do is, rather than writing the 3 bonds, sometimes we get really lazy and just write a circle on the inside, and that means 3 bonds. This ring is so common that it goes by a special name called benzene. So you can think of benzene as the suffix. We then want to have a branch name, and the branch name is right in the front. So I'll go ahead and I'll color that in blue. And we place that right in front. So if that's a ethyl substituent that's coming off, then it would be a ethyl benzene. If it's a bromine that's coming off and branching off, such as the example to the right, then it would be a bromobenzene. Now, a lot of these structures that I'm circling right now, these are so common that people get lazy and they like to have very easy names. So think of water, H2O. Instead of calling it dihydrogen monoxide for the proper UPAC term, people refer to it commonly as water. So these are all common names that the UPAC community have adopted, and so therefore if there's a methyl group attached, then the common name is going to be toluene. If there's what's called a alcohol group attached, then the common name for this one is phenol. If there is a amine group in H2, it's aniline and benzoic acid. You will have to memorize all of these common name benzene derivatives as they're classified. You will have to memorize all of these common name benzene derivatives. Often what we like to do is take these common name benzene derivatives, going back to slide 1, and we like to go ahead and add prefixes in front to really get lazy. So for example, let's say for example I wanted to go ahead and add a chlorine to this molecule right here, then we might actually, add a chlorine, and we'll add a chlorine right here. Then the methyl group would be number 1. This carbon right here would be number 2. And therefore we would call it 2-chlorotoluene. Let's go to this one right here. Let's say we wanted to add a ethyl group at this location. Making all of this benzene derivative common name as a branch, then a ethyl located at this direction, and I might as well use blue. We would call this a, let me go ahead and pop this up really quick. We would call this a 2-ethyl phenol. So there's a lot of variety that you can use when we name these. So you have to be aware of those. Now, we have another way of naming. And scientists get lazy. If we know we have branches, such as two branches you see here, instead of calling it a 1,2-dibromobenzene, we might actually call this ortho. Ortho. And ortho means that the branches are close together. Instead of calling this example in the middle 1,3-dibromobenzene, if there's a space in between, then you refer to this as meta. And finally, instead of calling this a 1,4-dibromobenzene, we get lazy and we call this a para. So P for para. So again, ortho, meta, and para. So we have multiple choices on how to name these. Again, in this example right here, I can choose to call it 1-bromo-3-chlorobenzene, or I can call it meta-bromo-chlorobenzene. This really only works for two branches. If we have three branches, then we have to do the traditional numbering and using di and tri. If you have more than two, then you would number in the direction of the branches. I pretty much won't give you those. I absolutely love these examples right here, along with going back to slide 9, these examples over here. So make sure you know those. Now, what happens if the phenol what happens if the benzene molecule is a branch or a substituent? Then it goes by a brand new name, and the new name is phenol. And the phenol is a prefix. So in this case, if this is the parent, which I'm circling in red, P for parent, then the branched phenol would be the suffix right in front. So that benzene molecule, again, if it turns out we use it as a branch, then it has a brand new name, and I'm highlighting the name right now up top, phenol. So in this case, this would be a 4-phenyl heptane. Oops, that's messy. Let me go ahead and go back to using red again. So it would be a 4-phenyl heptane. If there were two phenols on here, then it would be a 4, I know I'm getting kind of messy, but 4, 4-diphenyl. That says right here 4, 4-diphenyl heptane. So you should know those as well. Going to slide 12. Here we see a cool animation where we have a benzene that's passing right through a lipid membrane. So I'll wait for it to pop up again. Here we have again, benzene ring passing through a lipid membrane. Notice some particles require a membrane protein in order to facilitate the passing of it, such as this particle right here. Other ones just can't pass through at all. But anything that contains a benzene ring, which is flat like a penny, will slide right through the lipid membrane. Hence we call this lipophilic. And in summary, FYI, just like alkenes and alkynes, they're nonpolar, therefore insoluble in water, soluble in gasoline. And because of the aromatic effect of the spinning pi electrons, they are very chemically resistant and very stable. So this concludes our Chapter 1-2 Part 2 handouts.